making a homemade lathe. Today is part 5, which is looking at construction of the bed. Obviously the most important part of the machine, at the very heart of the machine, so this is where we're starting as we look at the design process. I would recommend that you go back and look at video 4 if you haven't already, which is really about the specification for the lathe. And I think that's important because on a project like this, which is likely to take a lot of time, months if not years, then it's worth having thought through some of the basic whys and hows and what it is that you're aiming to achieve before embarking on something and then discovering you need to change your mind or backtrack, which would be very discouraging and could be costly.
So it's entirely appropriate that as we get into the design of our lathes, that we start with the bed. And this is obviously the heart of the machine. This is what everything else hangs on and what gives the machine its rigidity and its structure and provides alignment for the various parts. So looking around on the web, particularly on YouTube, there are quite a number of approaches to producing a bed for a lathe, and we'll just touch maybe on a few of those, and also with examples of commercially built machines, which I think is always a good place to start. And I decided to break this section down into 4 parts. The first is the structure. I think it's helpful to look at the bed of the lathe as a structure holding everything else together. And then we're going to look at perhaps a little more briefly the manufacture, various ways of making a bed, particularly from the domestic context, from your home workshop. And then a little bit on materials. I think it's important that we do think about the materials we use and their compatibility with each other, and also alignment. And this might be where a lot of people start with the bed, but I think this is only one of various considerations. But we're going to certainly look at that and considerations that you need to take into account to provide good alignment. And the first example of structure that I've chosen actually is this rather nice little Bowley watchmaker's lathe. And this is interesting. It actually has a cantilevered bed, so everything is supported off the base of the headstock effectively, or from that end, which is typical of watchmakers' lathes. And it also has a triangular bed, which is interesting. But it wasn't only watchmakers' lathes which used a cantilevered design. This is a Drummond 3.5-inch Drummond from the beginning of the previous century, and you can see very clearly there that it's supported off one single footprint under the gap. And you might like to think about the advantages and the disadvantages of that design. I can think of one big advantage, which is that mounting is relatively easy, and twist is eliminated from the bed because you don't have a separate foot at the far end. So that's one obvious advantage of this design. I'm not aware of modern lathes which have this approach. You might be aware yourself. If you do, then please put that in the comments. Here's another structure which you might like to consider for a lathe. This is a 4-inch Drummond round bed, and this actually was the first lathe I had. Not this particular model, I had the long bed version of this, and it served me very well from the age of 13 until, well, for quite a number of years. And I did a lot of work on this lathe, and I learned probably my basic machining on this lathe. Obviously, this layout is designed to reduce cost. It's much easier to grind a cylindrical bed than it is to make a bed with V-ways or dovetails. So that's one consideration. There are other considerations, however, too. One neat aspect of this design is that the lead screw is actually up through the center of the bed, so it's protected from swarf and dirt. And there is one other feature which you can see from this view underneath, and that is that the saddle is actually able to rotate around the bed as the nut which holds the key in place is slackened. And that feature was advertised as being a feature which would enhance milling in the lathe, because what it does is it effectively changes the center height. And actually I use that feature on my lathe. It was a useful feature. Can you think of any limitations with this design? There is a limitation, and the obvious one that I encountered was anywhere in the keyway would be magnified, would be amplified as a movement at center height. And the proportions of this lathe, well, it's a 4-inch center height. I think from memory it was about a 4-inch diameter tube. So that means the mean diameter of the key from the center line, about which the whole saddle rotates, is something like, what would that be, 1 3/4 inches. So you've got 1 3/4 inches controlling the rotation by the key, and you've got 6 inches from the center line of the bed to the tool height. And that did indeed, in my lathe, result in it not turning parallel. So looking at the drawing which I produced for the introduction to the video, this is a Spencer lathe, and I own one of these for a number of years. An unusual machine because the saddle is in fact supported off the front face of the bed. There's a dovetail there running the length, and that means that the saddle can move virtually the entire length of the bed, and so can the tailstock, because it's on the upper surface of the bed, and they actually, as you can see here, they can pass one another. You could actually have the tailstock right up against the headstock and the saddle completely out of the way on the right hand side. You can perhaps get a better idea of the layout from this photograph. You can see that the dovetail on the front is actually rather deeper than I showed in my picture, but it gives you an idea of the layout. Interesting machine. And you can see there more clearly the V-ways on the front of the bed, the dovetail. What are the disadvantages? Well, I can think of one disadvantage. Swarf and dirt is going to accumulate in the top of the dovetail there. The lead screw is fairly protected, but the rack for the rack and pinion is quite low down. So that it's always good to have the motive power or the force propelling your saddle along as close as possible to center height, and this of course is quite a long way below. Another concern I had about this lathe, and I was aware of it at the time, is that the vertical load on the top shear is quite high for the area, the supported area it's got. In other words, the pressure is quite high, and I think that caused quite a lot of wear on the top part of the dovetail. However, this arrangement was used on some very expensive and high precision lathes. This is a Rivet 608 from the early 1940s, and that also has a dovetail on the front of the bed with separate ways for the tailstock. You can see from this photograph a little more detail. What's intriguing to me is the high degree of finish that's gone into this machine. You can see the hand scraping marks. What a lovely machine, in fact. So here we have a satisfactory design, a successful design. In fact, the way that this lathe was designed, it incorporated a lot of surface area, and they claimed that it was very rigid. So there we have another design. So now we come to part 2, which is manufacture, and this is probably where most of us with our home workshops are going to face the biggest limitations and constraints on our design. And there are a number of solutions which YouTubers have adopted to constructing lathes. I haven't included Gingery's approach with his lathe, which is based on aluminium castings. But here we have Debby Novrinal's lathe, which is a very substantial machine. You can see here that the ways are partly welded and screwed together, and you can see that it looks like a good substantial design. The only comment that I would make about this construction with socket head countersunk screws through the top of the shears is that this is an ideal place for swarf to collect, and I suspect that this is going to cause a lot of wear and could even cause fouling if you get swarf dropped in there half in, half out. So I don't know whether he resolved this issue, whether he decided to fill in the holes, but I've noticed this on a number of designs that this construction has been used, and I think it's something that should be avoided if possible. Now, on my own lathe, which I made from an H-section girder with a 1/4 inch steel plate on top of that, followed by the two ways, I decided to fix them with bolts from underneath. So you can see one bolt head there, and that way the top surface is completely clear, smooth. There are no holes or anything for swarf to fall into, and my lathe has given a good surface over, as I've mentioned before, a good many years, at least 20 years. Now, the other thing to note is that a lot of constructors use mild steel everywhere, and I think that's another thing which should be avoided if at all possible. And in my design, I opted for mild steel for the bed, for the ways, and I used cast iron for the saddle, and as much as possible of the rest of the construction. And that has the advantage of two different materials working together, which work together well as a bearing surface, and it's given good wear characteristics, I would say. Here we have another example of a Bowley watchmaker's lathe with the triangular bed. Now, there are several advantages with a triangular bed, especially if you are making one by hand. I'm not suggesting that this was made by hand, but it's worth considering if you are making your own lathe. Now, it's also noteworthy that some of the first engineering lathes, metal turning lathes, used triangular beds, and in fact Henry Maudsley's screw cutting lathe, purportedly the first screw cutting lathe of 1797, which you can see, I believe, in the Science Museum in London, employs two triangular beds. And I would imagine that starting from first principles and having to produce something as accurate as this, a triangular bed is a good starting point. You get straightness, you've got only three surfaces to work on, and yet it also gives you location. So that's something certainly worth considering. Now, in his channel, Let's Learn Something, a totally different approach is adopted, and he opts for linear bearings, and you can see linear bearings there for the ways of the bed and also for the ways of the cross slide. Now, my only comment about this is that whilst the linear bearings are in and of themselves superbly accurate, they are dependent on their accuracy over the length of the machine and what's underneath it. And since what's underneath is obviously very rigid, made of steel, I think that setting this up is going to be less than easy. Now, it could be that over small distances, say 1 inch or 2 inches, say 25 millimeters, 50 millimeters, the error isn't particularly noticeable, but I would imagine over a long length, like as is shown here, I think it would be very difficult to realize the actual potential of the linear bearings. So that's something worth considering. Now, a very interesting solution to this problem I came across in Joerg Beigang, forgive my pronunciation if that's wrong, in his channel. And he wasn't making a lathe. I believe he was making some metrology equipment or a milling machine, I'm not sure. But he used epoxy resin with sand to produce the structure of the lathe. And what he was able to do was, in the process, he was able to embed straight flat surfaces, as is shown here. And the advantage of this is that you have a construction technique which gives you flexibility through casting to get any shape you want over quite big structures as well, potentially, whilst maintaining accuracy and actually fully utilizing, I think, the potential of the linear bearing. So I think this is a really good solution to that problem. And apparently it's dimensionally stable and is a good approach. So that's something worth looking at, and I would highly recommend his channel. Now, whilst we're talking about materials, and this does in a sense cross over with construction techniques, it's worth also bearing in mind one radical solution which was adopted in the Second World War. And here you see, it's a very poor quality picture, I'm afraid, but you see a lathe with rather unusual features. You notice the webs and the weight, the mass of the tailstock. And that's because it's made of concrete. So this was a technique used in the Second World War to boost production. And these lathes could be turned out quite quickly. Of course, the critical components, and especially the sliding components and bushes and bearings, were all made from conventional materials and were cast into the concrete in the correct position. So there's a very interesting approach. And I have seen one YouTuber who has had a go at building a lathe using concrete, so that's worth looking up as well if you're interested. Now, this is another of my lathes, my ML7, which is still in storage at the moment. I hope to get it out soon. But of course, here we're using traditional materials, cast iron on cast iron. And this has a lot to be said for it, a tried and tested technique. But of course, the big problem is, can you produce iron castings, or can you produce big enough iron castings? And I suspect that for most of us, that is going to be a problem. Item number 4 on our list is alignment. And to illustrate the issue of alignment, I've chosen this picture of a Barker bar lathe. And you'll see here why it's called that. It has 3 bars which form the bed, 3 ground bars accurately located at each end, and the saddle slides along those bars. And also the cross slide slides on bars, as you can see here. The only question I have about this design is how rigid it is, and whether the lathe could be accurate, and whether you could take decent cuts without it chattering. Maybe someone who's used the lathe could comment on that. The other question I have is, using this kind of construction in our setting, whether it is practical because of the issue of redundancy. And that issue we're going to discuss in the next video. Now here's a variation on that theme. This is in fact a small lathe I purchased quite a long time ago. I didn't get around to renovating it or modifying it to suit my purpose, but here it is. Instead of having several round bars, it has 1 round bar and 1 square bar. And actually I think this is quite a neat arrangement, especially with the proportions of the length versus the cross section of the bars. So for its size, it strikes me as quite a robust arrangement, simple, and I think it will be quite effective. If anyone can identify the lathe, I'd love to hear from you. I haven't yet been able to identify it. Here it is in another view. You can see how the saddle and the tailstock operate with the lead screw in front of everything. Very simple, but it'll be fun to have a go at using that. Now here we have a Myford ML10, and this is a smaller version of the ML7. I think it was 3¼ inch height, center height, and as you can see it employs a dovetail on the top surface both for the saddle and for the tailstock. And you might think, well, this is a cheaper alternative to other arrangements and is therefore limited to hobby type machines, not industrial machines. Well, actually that's not the case. Here we have a very high quality Bowley lathe from 1925, and you can see there that that also employs dovetail surfaces for the cross slide, for the saddle and for the tailstock, albeit with a gap down the middle. That was not this is not just an option for cheaper lathes, it is actually used on high class machinery as well. Now here we have a very interesting machine. This was produced by Rolls-Royce in their engine aircraft engine division, and it was one of a small number of lathes produced for a very specific purpose, and there are only a handful of them around apparently. This is an interesting design. The saddle actually moves along a prismatic bed. Its front shear is facing us, it has support from underneath and on the rear side as well as on top. So it's actually gaining support from 4 sides of a prism. And obviously this was designed for accuracy, for precision. But the other feature about it is that it also has a dovetail on top, which you can just see in this view. That dovetail is exclusively for the tailstock. So the tailstock has its own support mechanism and the saddle has its own. So there's an interesting alternative. Now here we have what most of us would be more familiar with in the bed of a reasonably sized lathe. This is in fact my Colchester Student Mark I when I was renovating it, and we can clearly see here the arrangement of the bed. So the saddle sits on the front V, clears the rear V and sits on the rear flat surface. It also has a location underneath to stop it from lifting, as it does on the front. So the tailstock sits on the rear V and also on the front flat surface. So you have 2 independent location devices, and that enables maximum use of the space of the bed. But this really introduces the next topic which I want to cover in my next video, and that includes the idea of redundancy, or how to avoid redundancy and how to ensure that you have good location without the possibility of binding. And I think that's a potential issue with some of the designs that we've looked at today. So that will be the subject of the next video.
Well, thank you as always for joining me for this video. If you appreciated anything that was said here, then please do give me a thumbs up and consider subscribing if you wish to receive more similar content.